Okay, so to find the area under this curve, there's a couple easier ways than what I'm about to do, but just for the practice of this, using this limit process, if I wanted to, it always helps to graph. So I'm going to graph this guy, negative 4x plus 8. That's the value of 8, sloping at negative 4. Doesn't have to be super accurate. We'll call that 1, and it keeps going. Not the best graph, but it gives you an idea because I'll use this to help explain this process. This is a complicated process, one of the more difficult things we do in this class. Okay, so let's take a look. The idea here is we break this interval from 0 to 1 into a bunch of rectangles. These are rectangles. All right, so actually they're going to be left-ended rectangles, and I'll explain why as I go through this process. So the formula that you have, you take the limit as the number of these rectangles goes to infinity, and you're adding them up as your index goes from 1 to n, and then each height is represented by the function with some kind of input times the width of each of these rectangles, right? It's a simple formula that is the area of a rectangle is length times width. Okay, so the width is your change in x as you go through, and then this sum means you add them all up. Okay, and then this limit means you take the limit as n goes to infinity. It gives you the exact area under the curve. All right, so I like to start with delta x. What's delta x? Well, your interval length, the tire length is 1. Right, we have a little formula for that. That would just be like the upper x bound minus the lower x bound divided into n equal subintervals. In this case, that's 1 minus 0 divided up into n equal subintervals, okay? So that's 1 over n, that's delta x. This guy right here is going to be 1 over n. Now, what about this? I need to plug in a certain x value that's going to give me the height of a rectangle, and then as I goes from 1 to 2 to 3, it's going to move through this interval, okay, and give me a bunch of heights of a bunch of rectangles. Multiply them each by the width, add them all up, take the limit as n goes to infinity. So if we're starting at 0, these are typically the easier case. If you start at 0, right, and the width is 1 over n, then this little c sub I or x sub I is going to be 1 over n, the width of each of these times I. Okay, now how does that work? Well, when I is 1, it puts you right here, and then when I is 2, it puts you to the next end, and then when I is 3, it puts you to the next end. It just goes through. Okay, so this will always work if I start at 0. Right, we can use this kind of formulation every time for the width of an interval, and then you just multiply it by I to get to move through the interval as I changes. Okay, I'll do an example next where we don't start at 0, which makes this a bit more complicated. All right, so let's see what I got so far. I got the limit, the area is equal to the limit as n goes to infinity of the sum, I goes from 1 to n, of my function evaluated at 1 over n times I, or I over n would be a little bit easier. So that's negative 4 times I over n, that's my input, plus 8. That gives me the height of each of these rectangles. That's the height, right? The function value is the height times the width. All right, so this formula will give me this exact area for this shaded region. So let's see how we can knock those out. So I'm going to just, let's do this. Let's save ourselves a little bit of trouble. Call this S sub n, and then we'll take the limit as n goes to infinity. So S of n, I should say, equals, and then we'll do a little bit of algebraic manipulation for this guy. That's going to be, we want to isolate the I term, right? Because you have formulas. I'll put the formula up here in a second. For example, here's a formula of I. All right, if you just add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to n, a result would be n times n plus 1 over 2. Okay, that's one of your formulas. And I give you these formulas. There's one for I squared, there's one for constant, there's one for I cubed. That's it. There's just 4 of these formulas. Okay, so there's one of them that we see a lot. So what I want to do is find that in my problem. Okay, and the other one I can see I'm going to use in this one is the one for constant, and this should make sense. Right, if you just have a constant here, then what happens is that just means you're not plugging in an I. That's just C plus C plus C plus C plus C n times. So that's just C times n. Okay, so that's 2 out of my 4 formulas I'm going to use for this problem. So I'm looking for this, so I can apply the formula. And I'm looking for this, so I can apply the formula. Okay, so I can see I got an I here. So I'm going to actually factor out the negative 4 and over n. I'm allowed to do that. That's good. And then I have a plus, and then I got this, let me try that again because I forgot to run this I through. Give me one more step here. Oh, let's see. Let's see, give me 1 second. Okay, here we go. Let's take a couple more steps. So I forgot to run this 1 over n. So let me do that real quick, and then we'll see what we're looking at. So I got a negative 4 times I over n squared plus 8 over n. Okay, so that's what happens when I run the 1 over n through. But the n doesn't have to be in that summation, right? Because the variable, if you will, or the index is I. So I'm allowed to factor that guy out. So let's try that. I'm going to factor out the n squareds for both of those. I'm going to write 2 sums. So see if you follow this. I'm going to move him and him out of the sum. So that's negative 4 over n squared. And this is the approach I always want to do for these. And I got I, right? That's what I was looking for. I want the sum of I all by itself so I can use this formula. And in this other summation, so plus, so this is the sum, well, I guess I should say the sum of a sum. So I'm allowed to do those like individually. In other words, I can bring in another sigma here, and then I'd have 8 over n, but I'm going to pull the 1 over n out and have the 8 here. Now, I could have the 8 on the outside too and add up a bunch of 1s. It'll work out the same way. All right, but the way I have it written here is so I can use that formula. Okay, so this is equal to negative 4 over n squared times the sum of I as I goes from 1 to n, which we have a formula for, n times n plus 1 over 2 plus, and this is just adding 8 to itself n times, so that's 1 over n times 8n. Okay, the n's cancel out. The 2 will cancel, so now I have, for my sum, I call this S of n, I have negative 2 times n plus 1 over n squared plus 8. All right, so now my area is equal to the limit as n goes to infinity of this thing, right, which I called S of n, which I've simplified to this after applying my formulas. So now I just take the limit of that as n goes to infinity. Okay, clearly that just stays at 8. And what is this equal to? Well, if you recognize that, if you run this through, you can see it a little more clearly. That's n squared plus n. So the limit of this as n goes to infinity is just equal to 1, right? Because you just focus on your leading coefficients, 1, 1. So that would be 1 times negative 2. So that's equal to negative 2 plus 8, which is equal to 6. Okay, and that's the process I would follow for all of those. It's not easy. My advice would be, if you're ever starting at 0 going to wherever, then these parts are always going to be the same. Like if I said on 0, 5 for this problem. Well, 5, let's try 2. 0, 2. Then the delta x would be 2 minus 0 over n, and the number I plug into my function would just be this times I. That'll always work for us. Okay, now, in the next problem I'm going to do, we're not going to start at 0, and we're going to see how to tackle that one. That'll be a little more complicated.